Okay, so just a real quick review on the quotient rule. I want to emphasize that you really should have this formula memorized. And just remember it's FG in order, and it's the first one derivative, the first function derivative, and then it's the second function derivative. It's negative with the quotient rule, and it's over g squared in the denominator. And the example that I gave last time was taking x squared plus x over x plus 1. And so I'm treating the numerator as a function, the denominator as a function, and then basically taking the derivative of the numerator times the denominator minus the derivative of the, the numerator times the derivative of the denominator over the denominator squared. And so we get this, and when we simplify it, we get x squared plus 2x plus 1 over x plus 1 squared, and if I factor the numerator, I can see that those things cancel out and I get 1. Now, just to drive a point here, the quotient rule takes a lot of algebraic manipulation, so where you can avoid that, you should avoid it. And so in this one, you recognize that the numerator factors, and we just have x times x plus 1 over x plus 1. The x plus 1's cancel, and even though x does not equal negative 1, we still have an equivalent expression for f at x at all other places. So we take the derivative of x, and we just get 1. So we get the same answer, but with a whole lot less fuss. Okay, so really always look at your functions and say, can you simplify this? Can you do this sort of thing where you're actually dividing through by the denominator, or what I show you on the board where you're factoring it and taking out the common factors. All right, so the chain rule, let's get to that. Now the chain rule looks really ugly and complicated, and when you see it written out like this, it's probably a whole lot worse than it really is. So what this amounts to is that if I have a composite function, okay, let's say f at x equals g at h at x. Okay, so to take the derivative of this, what I do is I take the derivative of g, and I keep h unchanged, and then I multiply it by the derivative of h. Okay, so when you see a couple examples of this, you'll see how this works. All right, so the first one, let's say we have this square root of x squared plus 1. Up until now, there's no way to take the derivative of this function. But think of this in terms of an outer and an inner function. Okay, so here's where a little color helps. You have the purple function, which is just the square root, and then you have the green function, which is x squared plus 1. So what the chain rule says is that I'm going to take the derivative of the outer function, which in this case is 1/2, and then whatever the inner function is to the negative 1/2. Okay, so that's just simply, you know, looking at the derivative of this outer function. So I'm going to put in the inner function and then take the derivative of the inner function and multiply what I've just done by that derivative. So then if I do a little bit of simplification, the twos cancel, and then the x squared plus 1 to the negative 1/2 is just the square root of x squared plus 1 in the denominator, and we have a x left over in the numerator, and so we have its derivative. So rather than think in terms of that first top, you know, f equals g at h at x, think inner and outer functions. Okay, when you identify that outer function, take the derivative of that without paying attention to what's the inner function, drop the inner function in the middle without changing it, and then multiply it by the derivative of the inner function. Okay, so another way to look at this, and perhaps this is one of the justifications for the chain rule, is that here's a function y that we want to take the derivative of it with respect to x. Okay, and so what we do is we can take the derivative of y with respect to u, which will be taking the derivative that's just doing the purple stuff out here, and then we're going to multiply it by the derivative of u with respect to x. Now look at these differential elements as kind of entities unto themselves, and you can see the du's kind of cancel here. Okay, so then we end up with just dy over dx. Now that's kind of sloppy arm-waving math, but it kind of works as a model to see why this thing works. So what we're really doing is we're taking the derivative of the outer function with respect to the inner function, and then we take the derivative of the inner function. All right, so let me show you a few more examples, and we'll get to doing some in class pretty fast. Okay, so here's an alternate way to do this function here. You can do this by substitution if this really bothers you, to look at inner and outer functions. So what we're going to do is first define this other function u, and we're going to say that that's our inner function. Okay, u equals x squared plus 1. So then y, or f at x if you want, but y, our function, is going to be the square root of u. So when we take the derivative of that, if we use this chain rule expressed this way, where we have dy du times du dx, okay, so I can take the derivative of y with respect to u, and then multiply it by the derivative of u with respect to x. And now I have some mixed variables here, so I want to go back and put my definition of u in there. And so I get exactly the same thing once I'm all done in simplifying it. So this is probably not the way you want to do it in terms of maybe defining a letter and then, or defining a function, this inner function, explicitly with respect to u. But towards the end of the semester, when we're going to do some integration, and we're essentially undoing the chain rule when we're going backwards, when we're finding the integral rather than the derivative, this will be kind of the method of choice for you to use, because it'll simplify things at least visually quite a bit. But hopefully you'll get the point here where I'm saying u equals this function. And so the derivative of f at x is going to be dy with respect to u, and then du with dx. So it's the derivative of u with respect to x. Okay, and we get to the same place. If I just hop back to the last slide, this is probably the more practical way to do it. What it involves, though, is that you keep track in your mind what the inner and the outer functions are. So you don't ever have to explicitly name one h and the other one g or whatever. That you're basically just looking at, okay, this is on the outside, I'm going to take the derivative of this, keep the inside there, then I'm going to take the derivative of the inside. Okay, so there's where we are. Another example, let's say I want to find the derivative of this now. So I have two ways to do this. I can expand this, okay? So I can take x to the fourth plus 6 times x to the fourth plus 6, expand that, and then multiply it again by x to the fourth plus 6. And perhaps when you're cubing something, this is like the break even. If if you're just going to square it, perhaps it's easier to do it, to expand it. If you have something to the 10th power, you don't want to get involved with that. So you want to use the chain rule. So the chain rule here is that I'm going to take the derivative of see what my outer function is. I'm going to consider 2 and then this expression to the third. That's my outer function, so I'll take the derivative of that. So the derivative brings the exponent down to 2, and of course we're multiplying the 3 times the 2. Keep the inner function intact, exactly the way it was, x to the fourth plus 6, and then we take the derivative of x to the fourth, which is 4x cubed. Okay, so there is the derivative, but now we need to simplify. So at minimum we need to collect the coefficients, and probably don't need to expand that expression. If you're going to put this in a calculator and calculate a number, it's probably easier just to first take x to the fourth plus 6 and then squaring it, rather than expanding it out fully. So I would consider this fully simplified, even though if you look in an old algebra book, they'll probably start with this and say, simplify this, and what they mean is eliminate the parentheses. Eliminating the parentheses isn't always the best thing. What we want to do is have as brief of a definition of the function, and at minimum collect all the like terms and the coefficients. Okay, and so we'll see more of that as we go along, and you'll get a feel for that. Okay, so let's do something else. Let's say we have f at x equals 1 over 2x plus 1 squared. And so here I'm going to write this as a negative exponent, because then I can use my power rule. So that outer function is just whatever, I'll call it u to the negative 2. And so we'll take the derivative of that. And then we'll multiply it by the derivative of 2x plus 1. Okay, so you see how I did that. I took the negative 2 is now the coefficient. You subtract 1 from the 2, from the negative 2 to get negative 3. And then once we're finished taking the derivative of the outer function, we look inside and we say, okay, what's the derivative of this? And it's just 2, because derivative of 2x is 2, derivative of 1 is 0. And so we have this. Notice I collected the coefficients, I got rid of the negative sign in the exponent, and so this expression for the derivative is comparable to this expression for the original function. Okay, any questions on these before I go along? Okay, so let's revisit the power rule with respect to the chain rule. Okay, so this is what I did on this last example, where I have some function u to the n, and I want to take the derivative of it with respect to x. So what I do is I use my power rule. So I use the n as the coefficient, subtract 1 from n as the new exponent, leave u alone, and then we multiply it by the derivative of u with respect to x. So this is just a restatement of the power rule. If you followed what I did on the last slide, then really that's all what this is saying, is that we're going to use the power rule on the outside function and just take the ordinary derivative on the inside, which is generally the power rule is what we use for the inner function as well. Okay, so we'll revisit this kind of function again, where we have x to the 5th plus 1 to the 4th. So the power rule with the chain rule says that this is going to be then 4 times that x to the 5th plus 1, and then we subtract 1 from 4 to get the new exponent of 3, and then we multiply it by the derivative of x to the 5th plus 1, which turns out to be 5x to the 4th. And then we collect our coefficients, and that's about as simple as you want to get. Perhaps now, I think I am leaving out a cubed. Yep. Okay, so you don't have to expand that cubed. We'll just leave that as a term cubed. Okay? Okay, so here's one for you to try. You try this one first. Okay? So I want you to try finding the derivative of the of this function, and it's possible to first square it and then use the power rule, but don't do that. Try and use the chain rule with this one, where you have that inner function and an outer function. Well, yes, I would do that, although I would be really, really reluctant to take anything away from you if that's what you gave me. Okay, I mean, this is that's a perfectly good polynomial expression, and to work that out, you're basically going to end up with 4 terms. So that's not too bad. Certainly on your homework, I would do that, for practice. But this at least shows what the derivative is. Okay, so here's another one. So oftentimes, something like this would invite using both the chain rule and the quotient rule. And so where you can, where you have something like this where it's 1 over a function, first simplify the function to make it so you can use just the power rule with the chain rule. And so on something like this, I would rewrite it as have an exponent to the negative 1/3, and then taking the derivative, we would have somebody's not keeping up here. Okay. So we have the exponent, which was 1/3, now becomes the coefficient. We leave the inner function alone, subtract 1. Negative 1/3 minus 1 is negative 4/3. And then the derivative of the inner function is just 3x squared. And then from there, we would write this to be in radical form again. So with to the 4th power, you could put that either inside or outside the radical. You have the same thing. And so we're good there. So there's not too much else to the chain rule except practice. The thing that I want to make sure that you do is that you're reading the textbook, and we're in Chapter 2, Sections 2 through 2.4. 2.4 is the chain rule. Hopefully you've at least browsed the other chapters. The difficulty with using any calculus textbook almost is that we're not going over things like logarithms and trigonometric functions and things of that sort. So you have to skip over those examples, and sometimes those examples are actually pretty good. But just bear with the text a little bit, skip over the examples that involve those. And then also notice that they're using not only the F prime notation, but they're also using that capital D as the operator to find the derivative. So that's useful to see that notation. And then, of course, here in the classroom and in the textbook, we use the dx notation for the derivative. So depending on what's the circumstance, you'll find one or the other of the notations a little bit more helpful.